some formulas. We were actual basic formulas we will use in the proof. Today I will give the proof of the classification of three-dimensional shrinking soliton. I mean gradient soliton, shrinker. So I will start with two propositions of Zhang and Chen and Zhang. So it is about the Ricci flow with vanishing y tensor. Of course, in three-dimensional case, y tensor is 0, so it's automatic in three-dimensional case. So the proposition is Zhu Hong Zhang. Since if the y tensor is 0, I start with the if G I J T is a solution to Ricci flow with equals to 0. At t equals to t0. Then, so when you have, this is the solution of Ricci flow. So we have the formula I need to put here. So and the formula is, we have Rm alpha beta Rm is a curvature operator, alpha beta plus, just make sure, square plus Rm. So we have for any point in M exists orthonormal base EI such that and this E and n numbers such that the base by alpha EI EJ, we can choose a base the base satisfies the following: Rm alpha beta equals to, actually this base is the base which diagonalized the Ricci operator. So it also diagonalized the Q. Usually it's called Q. So I think we have two here. Yeah. So it equals to, when alpha equals beta, that means phi alpha equals to j. So it is equals to mi plus mj. And otherwise is 0. So it is when y tensor is 0, so it's a good thing. You can diagonalize the R and alpha beta. Has a similar thing here. You have sum m I k m k j. K different from I j. This is when phi alpha. Similar thing here. And 0 when alpha divided by beta. So you can diagonalize the Q operator here. So in this case, you can get the inequality, which is similar to the one we used for scalar curvature. Remember that for scalar curvature we had minus Laplace R bigger than or equal to. We have this inequality for this. And remember that when we have another estimate, just like this, for distant function, bigger than minus 5 for x belong to some ball. When we have this, actually, if you check the proof, we don't care about the Ricci flow. Actually, we only need a function which satisfies this equation, and a distant function along the flow satisfies this. We have the estimate. That is exactly we needed in the proof. So, using this idea, John used the idea of Chen. They get this important theorem, which is very interesting. You generalize it for n m is a non-negative integral. It depends on. I consider 0 is not a natural number, so I put here. Exists Cm, a constant, M, G, I, J, T is a solution of Ricci flow is a solution to Ricci flow on the interval, which is similar to the last lecture. We have equal to 0. Assume R, X, T Ricci. I just assume a little bit stronger. This is bigger than, less than or equal to minus 2. That means that all the eigenvalues of the operator is less than this. For X, A, T. Or T in the interval. And there is a number r plus m. M is a new, bigger than or equal to minus km on the ball sometime time 0. Where mu is the least eigenvalue of the curvature operator. Then we have r x t plus m nu bigger than or equal to minus minimum minus cm t plus 1 over km minus cm square on the ball x belongs to x the half. It is an interesting. It's very similar to the theorem we proved in the last lecture. So the difference is that when m is 0, is exactly the theorem. So when m is a number, you can see this is the least eigenvalue. So it also satisfies some disequality like this, but you need some careful analysis. But you still have this kind of estimate. This implies that, remember that when m is 0, we can prove that you have if you have an Asian solution, you can prove that it's non-negative. So in this case, for the Asian solution, when the y tensor is 0, so you can prove that this is also non-negative. So why? So if it's negative, you can put m bigger here, because this side where it goes to 0. So it's a contradiction. So it implies that the curvature operator is non-negative. So as a corollary, for shrinker, Rm is negative because it is an Asian solution. So that means if we want to classify the three-dimensional shrinker, so we only need to deal with the shrinker with non-negative curvature operator. Now we have a look at the result of Hamilton. The Hamilton says that for gradient shrinking soliton for shrinker, with Rm non-negative, only have two cases. Either m, the Rm of m is strictly positive for any point, or m equals to n cross r k. where n is the shrinker with positive curvature operator. This is any dimension. So, so if n is compact, it has been classified. That is following from again and even. Now this. The n equals to 2 and 3 when m is compact. M has to be S2 or S3 and their quotient, finite quotient. When m when equals to 4, also due to Hamilton, it is S4, actually Sn and their quotient, and finite quotient. It's due to first Hamilton for dimension 2, and Hamilton, and then Born-Wakein. It's actually for dimension bigger than 6. In fact, Brenner has he only needs the curvature, the positive isotropic curvature on M cross R as the same result. So the compact case has been classified. So for three-dimensional case, it remains to prove that the only case is that non-compact, the positive curvature case. If you have so that is the result of the following theorem. If M, G, F is a shrinker, with Rm positive, of course, as a complete, that represents complete, then M is compact. So if you three-dimensional. So this completes the classification, because this is compact with positive compact with no negative only this case, and in three-dimensional case K and only can be 1. So if case 2, this N or R3, so you can classify it because we have already know there is no compact soliton on this kind of manifold because of the S1 here. The fundamental group is infinite, which is not possible. This result has a not very long history, but there are many results along the way. It's first proved by Perman using the under the hypothesis of long collapsing, kappa long collapsing, and use the bounded curvature. Because and something. Bounded curvature and non-collapsing. Of course, he put some curvature post. Yeah. The non-collapsing is necessary for him because he used the Gromov convergence. He need this condition to guarantee the. Also, the boundary curvature he also needed because he also need other beside the convergence. He also needs somewhere else, and the way to prove it is quite long. If you look at the book of Ben Chao and Lupin and Lillet, you can see the proof involve many details because you have to prove it's splitting. You need the topolog comparison theorem, and then you need to estimate the area. You need the Gauss-Bonnet. So when you use Gauss-Bonnet, you really need three-dimensional case because the never set is the surface. You use Gauss-Bonnet. So the proof I will give here is quite simple. We only need the formulas of Hamilton. The first paper of Hamilton about the Ricci flow, and we used some estimate of the potential function and the volume growth to guarantee that the technique is legal. So we just record the formula of Hamilton. Proof. Record that Hamilton proved that for this function is equals to terms F is the function. Oh. Oh, I still don't have this one. This is for Ricci flow. So 2 over R2 R gradient Ricci minus Ricci gradient R square and plus R over 2 gradient Ricci square R square R. We need some patience to look at this formula. R cube, where P is 1/2 lambda square plus where the lambda bigger than mu, is the eigenvalues of the curvature operator. So anyway, we only at this moment we only need that it's non-active. This is non-active. So to simplify the notation, I will call this U, and I will call this part, I will call it Q. And also I will define eta equals to R squared, which I will read later. So since we are working on gradient shrinking soliton, so it's a solution it's a special solution of Ricci flow. So the left-hand side can be computed. So actually we have the left-hand side is equal to, because you have two terms. One term is the direction of gradient f, and another is the scaling. Since the scaling does not affect, if you're scaling a scalar metric, it's the same. So you have this equal to gradient u, gradient f. So I will rewrite this form like so. On m, fixed m, we have Laplace u. I will move the next q to the other side, minus gradient u, gradient f. This is this term. I will put q on the other side, it becomes positive, and then we have gradient u minus gradient u. I will put here log r squared equals to q, which is non-active. So it's a direct computation. You can put a e. You can put this together, so you have divergence r squared e minus f e minus f and gradient u equals to q at no, I will do it slowly. I will do it. If you put a e minus f here, you put a e minus f here. So this e minus f goes to here, and here you can put it in. You have a gradient e minus f. I will put some more e minus f. So finally we have Laplace. Actually, we have a quicker. No, we have a quicker way to prove it. This I will do. This one is equals to Laplace u minus gradient u gradient log at, because you have log minus here, you have it's equal to q. So we have divergence. Gradient u equals to q is negative. So from this, we just put phi square. Put phi square u. It's divergence bigger than or equal to 0. So I put sign here. It's less than or equal to 0. I take integral of m. For phi, I need this compact supported. So it is equals to, you can, it's gradient phi square u, gradient u times at this less than or equal to 0. Is equals to, we do a quick repeat calculation. The square at, and we also have phi gradient phi u gradient phi gradient u times at. M here. It's bigger than or equal to. So we can see here, here's a phi square, phi, this one. So the bigger than or equal to, you have phi square. Just make sure. We have twice here. Yeah. We have it's bigger than or equal to this one, phi square. Gradient u square at, it's bigger than or equal to 1/2 phi square gradient u square at 2 u gradient u square at. So we have, this is half, we have 4 times u square gradient phi square at. Since we can choose any phi with compact supported, so if you choose phi, phi equals to 1 on the ball. We'll put R here, and 0, 2, and here you just make a connection. It's bigger than. Here, with gradient phi less than C over R on the ball to R. So we have ball R, because it's equal to 1, gradient at less than or equal to 4. This is u square. U square I will use that one. Reach R is I square. And because we know that this is bigger than or equal to R square, C. Put C over R square here. And this integral is on the ball. So if this goes to 0, so we have this equals to 0. So to justify if this goes to 0, we just to justify if this integral is finite on n. So we have already know that f has a quadratic growth, and we know that the volume is polynomial. And we can see here, because R, we have this formula here. Actually, this implies R less than or equal to F. You just drop the term gradient. So you have a quadratic growth. So this is exponential. This is quadratic, so it is finite. So it goes to 0. So this implies that it is clear, it's finite. Actually, well, I will talk it later. This kind of equality holds more general, without any conditions. So so we have gradient u equals to 0. That means that one goes to 0. It means q 0. Of course, R now is positive now. So when Q is 0, you have here lambda equals to mu, mu equals to nu. So it implies it has to be mu equal to nu equal to lambda. That means M is Einstein. Since it has positive curvature at every point, Einstein means that the curvature curvature is constant at every point. Since it's Einstein, so the curvature has to be constant. So it is compact. That completes the proof, the classification of three-dimensional shrinking solid. As we can see that the many result also holds when the wire tensor is 0. That means in high-dimensional case, that means conformally flat. So I would like to say something about the high-dimensional case. There are several results. First, without assuming the tensor y tensor equal to 0, the neighbor proved that two results in his paper. The first result is related to the lectures of Lahan. Proved that the soliton, the soliton with bounded curvature, shrinking soliton with bounded. I mean this soliton, not necessarily gradient soliton. The shrink soliton with bounded curvature has to be granular soliton. So this is the result. And another result, he proved that the 4-dimensional, non-flat, complete non-compact, shrinker with is isometric to S3 cross R, S2 cross R2, and their quotient. You use reduced length. You don't need conformally flat, but you need bounded curvature. In case tensor y equal to 0, the picture is quite clear. It has been proved by Lee Wallace. That you need reach bigger than 0, and the curvature operator less than or equal to, because when y tensor equals 0, you have a similar equations like this kind of things. So you can use the technique. Or the more or less the same tag. M, the universal covering, is Rn, Sn, or Sn minus 1 cross R. Because the conformally flat, they don't have. This condition. Peterson really proved that this can be replaced by Ricci spinning. Of course, if the y tensor is 0, this is automatic. Why? You see the remark. There's some remark due to Zhang. After he proved that the tensor y tensor is 0, the curvature is non-negative. So of course, Ricci curvature is non-negative also. So remember that the scalar curvature is bounded above by some CR. Scalar curvature is bounded above. The scalar curvature is the sum of sectional curvatures. All the sectional curvature is non-negative. So every sectional curvature is bounded above by this constant. So of course, the Rm is Ricci is bounded above by this. So this integral is finite. So it's automatic. It's it's an interesting thing. But anyway, he need W equals 0. We know that this condition is a strong condition. So the next step should be working on more general manifold without assuming Y tensor is 0. It seems that it's not very clear to work on this kind of problem, but there is a good thing I would like to put here, which is related to the estimate. It's a simple thing, but it may be useful in the future. I don't know. Is that this is always true? I will give a proof here. Proposition. It's true for shrinker. Without any condition. The proof is the following. First, we can see that this one equals to minus put here, yeah. Well, I have put it here, and this goes to, yeah. Since this is this equals from the Bianchi equality, we have this formula. We have gradient I. I put here R equals to twice here. So you compare this, you find that this is 0. Now, this is an important thing we need for the proof. So we just take a supported function. We just compute this kind of f. And this is equals to n phi squared j minus f equals to square r j. We use the equation. We have gij minus fij e minus f. Just using the shrinking equation here. So we have this one 1/2. This part is scalar curvature. E minus f minus, we have phi squared r j fij minus f. So I just changed the position here. Fij Rij. So this equals to 1/2 phi squared r e minus f because we have estimated it will guarantee this makes sense. Minus. So I were using divergence formula again. We just put this j to the other terms. So you have fi gradient phi square r j e minus f j. To notice that this is 0, this part, the gradient, this part is 0, so it only remains this part. So you see it here. So it's quite long, I think. So I just take it. It's equals to 1/2 r phi square minus f minus plus fi times twice phi minus plus. So this is less than or equal to, I copy this one. Less than or equal to, this is Ricci. This is, if you take this Ricci, norm of Ricci, it's gradient f. It's gradient, it's phi, gradient phi, e minus f. It's integral here. So this, we have r phi square here. We have Ricci other side, so it is less than or equal to this one. I will use this formula, this Ricci phi. So we have phi square Ricci norm square e minus f plus twice here is gradient f square again. We justify that this is the integral because we have, again here, the gradient f, we just drop this out because it's non-negative. We have this less than or equal to f. So this is exponential, this is polynomial. So it's finite. The volume is polynomial, so it is finite. So you can take a similar thing using the cutoff function. This goes to 0. This goes to 0 means that this one, because this is 1/2. That is one. So you cancel half with that one. You have the Ricci square e minus f is finite. It implies that it's finite. Furthermore, actually, you have a better estimate. You can have this Ricci square E minus F equals to 1/2 R E minus F equals this one. Because it's finite, I forgot to mention that. This is a polynomial, it's the same reason. So it's equal to this. Can you see why? Because you have, this is finite. You use again the computation here. Actually, I don't need this side. On this side, use again the computation here. This is finite, and you choose the supported function. Since this goes to goes to 0, so you can have this kind of. Actually, you have the equality. It is a good exercise to prove that actually you have more. You have, in fact, one can prove square minus lambda is finite for all lambda positive. So you just repeat the computation, you will find that you can prove this. Actually, I didn't mention that, but I mentioned it before. When you, it's automatic. When you curvature operator is positive, R is positive. Actually, R is strictly positive. That means there exists a number such that R is bigger than the positive number. It's come directly from this formula. Before that, and it's first discovered by Lady. He used the 1 or half page to prove that actually from the R is positive, you can R is positive, Ricci curvature is positive. You can see the R increase along the flow of F. So it's positive, strictly positive. So to conclude my lectures, I will give some open problems, which are very important. The first important thing is that now we have classification for shrinking soliton. So can we classify steady soliton, which is a conjecture of Pearman? Conjecture of Pearman M, G, F. So complete steady soliton. That is a curvature plus 0 with positive Is it true? He conjectured if then M G must be Brenner soliton. three-dimensional brand. Oh, what's the difference? So for static soliton, we don't have 1/2 here. The estimate of the volume and the potential is different. So if you assume the curvature is, for example, curvature is positive, you have this is minus f is convex. So the f has the maximum point in some region and then goes to minus infinity. So if you take e power minus f, it's not finite. Actually, you have examples with positive curvature here. So the way is different. So up to now, the best result is due to, again, another norm, the last lemma chain. Zhou and a chain, Huaidong Zhou and a chain. I have to put initials here, Q chain. So the chain I mentioned before is Binlong chain, BL chain. This is Q chain. And another one, H chain. Here is W chain. So there are many chains. So he proves that if, of course, the Y tensor is 0 now, but if M, G is conformally flat, locally conformally flat, actually, conformally flat, the conjecture is true. It's true. That means this case is a Brenner salt. The conformally flat here, because Y tensor is 0, it is equivalent to cotton tensor. Equals to 0. And another result, very recent, is on arXiv. The Brenner posting on arXiv, he defined some vector field, and if the vector field is not very big, the vector field comes from the Brenner soliton. When in the Brenner soliton, Brenner proved that is 0, and he said if this vector field is not very big, the norm is not very big, it's actually very small, then it's also true. But in general, it's open. Actually, this condition is not necessary here also from the result of Binlong chain. This is a relatively big question. Also, there are some small problems. Small means, in some sense, it maybe more. It's not very well known. Problem that we proved that for shrinking soliton, for shrinker, in general, we have the volume, the average of the scalar curvature, dr. The disk I defined using the rho function rho. This is less than or equal to n over 2. It is true. So is it true? Can one prove? this one, the average volume, dr, less than or equals to this one. If it is true, you can get lower bound of the volume of the volume growth of the shrinking soliton. All the examples indicate this is true, but we don't know how to prove it. One side we want to prove some rigidities. On the other side, we need to know more examples. That is the problem. Can one find? Is there any non-trivial? Non-trivial means you don't. It's not a product of Einstein. Non-trivial examples of shrinking soliton. Which is not Canadian. So all the examples we know up to now are Cayley manifold. So is there some non-Canadian manifold? Actually, because the soliton you don't have a standard tool at this moment for this kind of object. So sometimes it takes a long time to prove a result, and finally you find there is a short way to get the result, just like I showed here. But anyway, it's a good topic to train your tools in geometric analysis. So, any questions? My talk is here. Thank you.